Welcome to this sailing theory tutorial. My name is Julian. In today's video, we're talking about current. In this video, we're going to talk about what current is and how we describe it. We're going to talk about some of the causes of current and where we expect to see and experience current. And we're going to talk a little bit about fluid dynamics and how hydrogeography can affect the current that we experience. In a future video, I intend to cover how current affects a sailboat when it moves through the water. I'll also talk a little bit about strategy for sailing in current, especially for racing. So what is current? Well, put simply, current is the movement of water over ground. So how do we describe the current? Well, the first thing we need to know is that we're most often going to be talking about the water's surface. And when we define current, we're going to be talking about two parts of current. One is the strength, or the speed of the water, and the other is the direction that the water is heading. So if we were to represent that on a diagram, it would look something like this. Here we're drawing the mouth of a river from a lake to a river. And each of these arrows represents the velocity of the water or the velocity of the current at that point. The longer arrows represent a faster moving flow, and the arrows are pointing in the direction of the water flow. So you can see that when we're talking about current, it is important to talk about both the strength and the direction of the current. What causes current? Well, the first cause that we're going to talk about is gravity, and it's one of the easiest ones to understand. Water simply flows downhill. A second cause of current is tides. We're going to do another video on tides soon, but for now, let's just say water flows in and out from an ocean into a bay or some other coastal body of water. A third thing that can cause currents, especially in the ocean, is buoyancy, and this has to do with different salinity levels or different temperatures of water. So what we see on a really large scale is that water tends to circulate, and this is a current effect as well. And the last cause of current that we're going to talk about today is wind and waves. So let's say that we have a very strong onshore wind blowing off a lake. And if we have a mouth of a river or something like that, the wind and the waves can affect the current, and perhaps it could cause water to either flow slightly upstream, or if the wind's blowing in the same direction as the current, then the current might speed up. Now, to make things easy to conceptualize for the rest of this video, we're only going to focus on gravity as a driver for current. But what I want you to remember is that anything that we talk about in terms of geographic factors that affect the current are going to apply for other current sources as well, like tides. So here I'm going to draw a top view of two lakes connected by a river. I'm going to fill them with water, and we're going to say that water flows from Lake 1 through the river into Lake 2. So remembering that we're talking about gravity, we also need to see some sort of elevation or side view. So I'm going to draw it here. And for water to flow, we know that the water level in one of the lakes must be higher than the other. So we're going to draw Lake 1 with a higher water level than Lake 2. And if we connect them by a river, we're going to see that as we pass through the river, the water's flowing downhill. Of course, I'm exaggerating the slope here, just so that I can fit it all in the picture. So there are two important parameters that are going to define the way that the water flows downhill. One of them is the height, or the difference in elevation from the first lake to the second. The other parameter is the length of the river itself. Because gravity is driving the flow, a higher elevation change, or a bigger H, is going to correspond to a stronger flow. The sides of the river and the bottom of the river are going to be causing some friction with the water, and that's going to resist the flow of the water through the river. So the longer the length of the river is, or the longer the L is, the weaker we would expect to see the flow. So I want to illustrate that for you with an example. Here I've drawn the two lakes and I've separated them by increasing H's. So this top set of lakes, which really doesn't have a very big change in height from one to the other, would have a pretty slow flow. And you can see I've represented that by a small vector arrow. If we increase the height a little bit more, we'd expect to see a stronger flow. And I've drawn a little bit bigger vector arrow. And you can see that as the trend continues, if we separate these by a large delta H, we would see a very fast or strong flow. So you can say the same thing about decreasing the length of the river, L. In the top case here, we have a river that's separated by a long distance, and so I would expect to see the slowest flow in that river. Just below it, I've shortened the distance of L a little bit, and I would expect to see a slightly faster flow. And in this bottom example, we have the lakes separated by a very short river, and I would expect to see the fastest flow here. Now what happens if we decrease L all the way to 0? Well, we end up with a waterfall. In this case, a lot of stuff actually breaks down because the water is flowing as fast as it possibly can, and it's actually accelerating as it falls. And as the water accelerates, it tends to break apart into droplets. So you actually don't have a continuous flow of water over the waterfall. But we would expect to see the absolute fastest flow that we could experience for any change in height when the length separating the two lakes is 0. So we have a certain expectation of how gravity might drive current in a river. Now I want to talk to you about how we might measure current. I'm going to suggest to you that one way you might want to do this, with very simple tools, is to use a stick and a watch and to stand on a bridge. What we can do is throw the stick into the river and then look at our watch. And if we start a stopwatch and wait for the stick to pass through a known distance and then take the time, we'll have enough information to determine both the speed and the direction of the current. We can calculate the speed by dividing the distance traveled by the time it took to travel that distance. We know the direction from watching where the stick started and where it ended up. So we could actually do this out on the open water as well if we're in a boat. And if we're in a boat, it might be more convenient to turn our boat into the stick, so to speak. So what we could do is we could luff up near a fixed mark so that our boat would not sailing forward or backwards. And then we could start our stopwatch and let the boat drift. And after a certain amount of time, we can check our watch, see how much time has passed, and then we can look back at the fixed point and make an estimate of how far we've drifted. In that way, we could get a time and a distance term, and again we could come up with both a speed and a direction of the current. So remember at the beginning of the video, I drew this quick sketch, and I was telling you that the direction of the current is represented by the direction of the arrow, and that the speed of the current is represented by the length of the arrow. Now this diagram implies that different places can have different speeds and directions of current, even if they're in the same body of water. I want to talk to you a little bit about how and why that might occur. So one of the first things that I want to consider is the depth of the water. So let's talk about the depth of the water and how it affects the strength of the current. What I'm going to do is draw a section view of a river here. What you have to imagine is that this is as if we had taken a river and cut it lengthwise and installed a viewing window. So we're looking at a plane that includes the upstream, downstream direction. The gray at the bottom of the diagram is the river bottom, and the blue, of course, is the water. What I want to talk to you about is how the speed of the flow might change vertically in the river from the surface level down to the bottom. And to do that, we're going to consider a parcel of fluid. For our purposes, we can think of a parcel of fluid as an imaginary box that's holding some of the water that's flowing. We're going to shrink that box down really, really small and then treat it as if it's one object. An interesting thing about parcels of fluid is that they can interact with other parcels of fluid and their surroundings in a predictable way. So one of the interactions that we might see between parcels of fluid is a viscous friction interaction. And I show that here with parcel 1 and parcel 2 shearing against one another. This friction interaction is what causes the change in velocity from the bottom to the top of a flowing fluid. If we imagine 3 parcels of fluid, one at the top, one in the middle, and one at the bottom, I'm telling you that those 3 parcels of fluid would not be traveling at the same speed. In fact, the parcel of fluid at the very bottom of the flow that's in contact with the bottom would experience a condition known as no slip. When we have no slip at the bottom, it means that there's so much friction that it's dragged that fluid parcel down to a velocity of 0. Now this exists in a microscopically small region next to the bottom, but it gives us a boundary condition at the bottom of the flow. The parcel at the very top of the flow experiences what's known as a free surface. And if for the time being we ignore the effects of wind on the surface, then we would say that there's nothing at the very top of the flow that's going to be trying to slow this fluid down. So the parcel that's in the middle of the flow would be some speed in between 0 and the maximum speed that we see at the top of the surface. If we were to graph the speed of the flow versus the distance from the bottom, or the depth of the flow, we would see that it increases parabolically from 0 at the bottom to some maximum at the surface. So what would happen if we dropped the water level, or decreased the depth of the flow? Well, the shape of the velocity graph that we drew is a function of the fluid properties of water and the driving force and the flow resistance. The no-slip condition is still going to exist at the bottom, and the top is still going to be free. So we can say that the shape of the graph is going to stay approximately the same if we drop the water level. What we could say definitely would change, though, if we brought the water level down, is the point on that graph where we're going to find the surface. So if we bring our water level down and we look on the diagram, we can see that our maximum velocity that we would expect to see at the surface of the water is going to be smaller than it was for the deeper water. We can repeat that demonstration on the diagram one more time just to drive the point home. If I bring the water level down one more time, we can see that we end up with an even smaller Vmax because the point that we're crossing this graph is even lower, closer to that area with a lot of friction. So we can take that as an explanation about how shallow water leads to a weaker or slower surface current. And I want to remind you that when we're sailing in our boats, we're sailing up on the surface of the water, so it really is the surface current that we're most interested in. There is, of course, an obvious exception to this general rule, and I'm sure that some of you have already thought about it. So what about rapids? Well, rapids occur in an area in a river where the depth abruptly gets shallower. And when this happens, the velocity of the flow goes up, which causes a stronger current. To explain this phenomenon, we can actually use streamlines to visualize the flow. If you don't know how to draw and interpret streamline diagrams, I suggest that you go back to some of my airflow around sails videos. So to make this easy, we'll consider 3 evenly spaced streamlines at the beginning of the flow, and we'll assume that the change in the depth of the water isn't great enough to cause a bump in the surface level of the water. So the surface level is going to be straight and flat all the way across. So if we continue those streamlines, we remember that streamlines have to enter and exit and they can't intersect. And what that means is that they're going to be squished together as they go across the bump in the bottom of the river. If we look right at the bump in the bottom of the river, we see that the streamlines are spaced closer together. And to us, that indicates that we have a relatively higher velocity flow. If we look back towards the beginning of the diagram, we see that the streamlines are spaced farther apart. And that tells us that we have a relatively lower velocity flow. This is a situation where having a shallower flow could actually lead to a higher velocity. And like I said before, it's an exception to the general rule that I presented before. The effect that we see with rapids is the same as what we see when a river narrows. So to illustrate that, I'm going to give you a top view and fill in some streamlines. What we can see is that the streamlines end up closer together where the river necks. And just like before, we're going to say that anywhere where we have streamlines that are getting closer together, we're going to expect that we have a high velocity flow. And when the streamlines are spaced farther apart, we're going to expect that we have a low velocity flow. So if you have an area where a river gets narrow, you can expect to see that the flow is going to speed up in that narrow stretch of the river. So we've spent a bit of time talking about what might affect the strength or speed of the current. Now let's have a quick look at some directional effects. So the first thing I want to talk about is the shoreline. In this picture here, we have a shoreline that's not perfectly smooth. We wouldn't expect that the current would follow each of these jagged turns in the shoreline. What we would expect to see is that the current would take some average of all of the jagged bumps in the shoreline so that it can smoothly flow from one side to the other. We would also expect to see the same thing on the other shoreline, averaging out the little bumps. And somewhere up the middle, we would have a flow that splits the difference and follows almost the natural direction that we drew on the page. The second thing I would like to talk about is obstacles in the flow. So in this flow, we could assume that if we're reasonably upstream, the current is going to be all flowing in one direction on one side of the page. As we approach the obstacle, we would expect that the current would take a turn around the obstacle. We would expect to see the same thing to a smaller degree from the intermediate current. And far from the obstacle, we would expect to see very little change in the direction at all. So the closer you are to an obstacle, the more likely it is that the direction of the current will be affected by that obstacle. So the next thing that we're going to talk about are eddies. Now, eddies are swirling or reverse current, and they occur in areas where the flow is perturbed. The first example of an eddy that I'm going to give you is a small stream ejecting into a lake. So we know that the flow from the stream is going to be coming out basically straight along the stream. And as it enters the lake, it's going to have to slow down because the lake is basically not moving. For that flow to slow down, it has to give up its momentum to some of the water in the lake. So as the flow from the stream is slowing down, some of the water from the lake is speeding up. But as the water from the lake is speeding up, it's doing it adjacent to another layer of water that's moving much slower than it. And every time you have water moving faster with slower water next to it, there's going to be a viscous interaction there. And the friction from the slower moving water beside the faster moving water is going to steer that water hard towards it. So what we end up with is a flow path that bends away from the straight line. And as we're bending like that, sometimes we curve all the way around and we end up with a reverse flow situation along the shoreline. So this can occur whenever you have a situation where a stream is discharging into a body of water that's not moving. For another example of an eddy, we're going to go back to the example of an obstruction in the flow. But this time the pier is not symmetrical. It extends out and then it ends abruptly. So what we would expect to see is that the current is going to flow around the first side of the pier, similarly to how it did in our example on the last page. But when we get to the other side of the pier, again we encounter a situation where we have flow at some speed and it's right next to flow that would be at a zero velocity. And that's going to be pulling this flow towards it. And so again, we could end up with a situation where we have reverse flow or a circulation there. The last example of an eddy that I'd like to show you guys is when we have a Y, the opposite of a fork in a river. In this situation, we have two streams mixing, and the top stream needs to change direction as it encounters the bottom stream. And when it does that, we could run into a situation where we have a recirculating flow bubble that develops right here. So I'm going to go through and circle in orange all of the eddies that we've found. These aren't the only directional effects that exist, but they're a good start in getting to understand how water flows and some current effects that we would expect to see in rivers and lakes. This concludes my video on current. In this video, we discussed what current is, how we define it, what causes a current, where we expect to see current, and what factors affect current, both in terms of its speed and its direction. Keep your eyes peeled for a future video where we'll talk about current affecting a sailboat and some strategy for sailing in current. Thank you for watching.